Okay, today we're going to talk about what's called science skills or science process skills. These are something that not only a scientist needs, but any student or any person needs, because what you're doing essentially is trying to figure out about the world around you. This is something that anyone can do at all. So what are those science process skills? What are those skills that you need to do science? The first one is what's called observation. We'll talk more in detail about this later, but essentially this is using your five senses to experience something in the world around you. The second one is identifying variables. So after you've made an observation, you need to look at what it is that's affecting that observation that you see. This is going to lead to what you end up testing. Hypothesis writing, a critical part. This is where you actually determine what the cause and the effect is, and you actually make a prediction. This is something that has to be measurable. So you should say, okay, if I do this, then this is exactly what will happen. That's how you determine if your original idea is correct or not. Then you actually run the experiment. This is testing your hypothesis, your idea for explaining the world around you from your observations. And then the conclusion is the end part, and this is where you say, okay, my original idea was this. When I ran the test, this happened, and this either supported or didn't support my hypothesis. That are science process skills. Now, we're going to take a little sidestep here before we move into some detail on all these, and it's a very important point, and I think actually depending on what level you teach with students, and I know certainly teaching high school students that this is extremely valuable to me, but you have to hit this on the head. You have to have students understand, and as a class, you have to come to a consensus as to what is science and what is not science. And so this is a good discussion to have with your students, and you have to go through this. So the first part is that you need to understand, and they need to understand, that science is testable. It has to be something that we can test. And I'm going to get a little bit further into this later, but I will make this point right now that essentially what we're saying is if you think, for example, in Flathead Lake is some sort of monster, well, then to make it testable, what you have to do is you have to say, well, okay, what I really want to know is how much the Flathead Lake monster eats on a day-to-day basis for a 2-week period. And so what we're going to do is analyze the amount consumed and what it eats and where it eats. And the real problem we run into and why it doesn't become testable is that we can't find the Flathead Lake monster to do it. So that makes it a little tough to do. So we have to have evidence. Science, in order to be testable, has to be based on evidence. We have to have something that we can measure, record, compare, and that makes it science. So with that evidence, we have to be able to conduct an experiment. We have to, again, if I use the Flathead Lake monster as an example, we have to be able to find it, number one. We have to be able to observe it, number two. We have to be able to measure what it's eating and the amount that it's eating, and that makes it testable. That makes it an experiment. Another example of this that would be testable would be how many drops of water you can fit on the head of a penny. And so we can actually test that. We can put a penny on the table, we can use a dropper, and we can drop drops of water onto the head of the penny until they flow off, and counting the number that we have. That's something that we can run an experiment. It can be testable and measurable. The interesting thing, and actually really one of the coolest things about science, is it's not absolute truths. It's not facts. A lot of people like to say, well, science, it's a fact, or that's a fact. And when you talk about facts, it might be that a cheetah can run 60 miles an hour. That might be a fact, but that's not a scientific fact. What science is based on is best explanations on the evidence that's available at the time. There are so many examples of things that we used to think, and then we don't anymore. The flat Earth is one. We don't think the Earth is flat anymore because we have more evidence to support the fact that it's a sphere. Uh, Scientists used to think in order to correct some severe mental problems that they cut out the frontal lobe of a person's brain, and we understand that that's not very good right now. And there are some things that we don't understand yet. Scientists don't really know what the appendix is used for, but it doesn't mean that they don't keep trying to learn that. Scientists don't know what junk DNA is for, but it's a huge part of our DNA, and they sure want to know what it's all about. The giant squid that lives in the ocean, we have only like a minute and a half of video of it and only a few dead squids that have washed up on the shore to study. And so we have a tremendous amount to learn about that. And it doesn't mean that scientists don't stop trying to do that. But they're going to base it on evidence and the best evidence that they have to create that explanation. They're always shooting for that best explanation based on the evidence at the time, and it can change if new evidence arises. Astronomy is a great field. We're always advancing our technology and learning more and more. Now, what are we balancing this against? Oh, last thing, I'm sorry. Uh, when we talk about science, a lot of times the word theory comes up, and people say, well, oh, it's just a theory. But you really have to hit home with your students that theory is an incredibly important tool in science. You can almost think of it to a scientist, it's not something like it's a throwaway. Oh, it's just a theory. It's something that we don't care about, or it's not that big a deal. It's a huge deal because theories have been studied for decades and sometimes over 100 years, and every test that's run shows that it's been supported. The evidence is huge in favor of this. It's so big now that scientists can use that theory to make predictions about other things. A great example is the theory of plate tectonics. We say that plates move. Well, now if we understand that plates move and we have a lot of evidence that supports that, then we can say, well, maybe plates moving causes earthquakes, or maybe plates moving leads to volcanoes. These are the things that can be made predictions from theories. So don't ever say it's just a theory. Theories are powerful tools used by scientists to further our knowledge. And what are we balancing all of this against? We're balancing this against belief. Beliefs come up a lot in class and a lot in discussions about topics, and people want to use those. And there's all kinds of different beliefs. I mentioned the Flathead Lake Monster. You could believe in Yetis. You could believe in aliens. You could believe in a higher being. It doesn't matter. Those are all beliefs. And the difference between a belief and science is the lack of evidence. Beliefs are perfectly okay to have. I have a belief system. I've developed it over years and years of my life, and so have you, and so have your students. And it's not your job to change their belief system. It's okay to have beliefs. The difference is this. Even scientists have beliefs. They believe that this recent Pew study from the Pew Research Foundation, I know it's a funny name, but they showed that 51% of scientists believe in a higher power, and they still do valid science. It's okay to do it. Lots of people do it. But the important part to remember, and your students and you need to know this, is that beliefs are not answers to scientific questions. If we can take that and find evidence, then yes, but you can't just say, oh, it happened because the Flathead Lake Monster swished his tail and scooped out the Flathead Valley, and that's how the valley formed. That's not a valid explanation. So that's just important, and that's one thing that we need to know before going any further. Now what you're going to do